Knowledge and understanding are the keys to the real truth. Hey everyone, this is Kevo and welcome to another video for Right Side Up, the truth review channel for you. Whilst doing some recent research, I discovered a few things about the curvature calculators that are being used to argue both for and against curvature of the Earth. The first thing is that I could not find a calculator that showed me all of the figures that I wanted to see all at once. The second thing I noticed was that some people are misinterpreting the data, and the third thing is that the calculators themselves were not accurate. They are giving incorrect results. Stay with me as I show you the quick check that you can do to see if a particular curve calculator is correct or not, followed by an introduction to and an in-depth explanation of my own all-in-one curve calculator, so as to give you a better insight into what measurements are relevant, what calculations are required for which measurements, and how to apply the results. Okay, first things first, checking for accuracy. Pick a curve calculator and based on the radius that is used for that calculator, find the circumference and then type into the distance field 1/4 of the circumference. In this case, 6,288.78265778 miles. The result for the drop should equal the radius, and in these examples it does not. Dr. Zach has a spreadsheet calculator that looked like it could have potential, however, it too is inaccurate. There are several point-to-point measurements that can be determined when scoping the horizon for curvature, and some of these results are sometimes misinterpreted. This is the diagram that I created to accompany my all-in-one curve calculator. Each band of color represents a point-to-point measurement that is determined by the input of any or all of three measurements: the radius, the height, and the distance to the target. For the purpose of the Earth's curvature, the radius is set at 3,959 miles. But remember that in this calculator, the radius is able to be changed. I am by no means any form of expert in the field of math, and I admit that I had to search for answers so as to understand and formulate the necessary equations within a spreadsheet. I am using OpenOffice, and some of the functions require additional commands to attain the correct result. I think Microsoft is a bit different. The results are derived from two triangles, so the calculator can be used as a distance to horizon calculator, a curvature calculator, or an all-in-one calculator. The first set of formulas for this calculator are off to the side here. Perhaps there is a way to condense these formulas, however, I found that laying them out over several fields rather than stacking them all in one field was the way to go. The individual formulas are intertwined with each other in a way that produce accurate results with an adjustable radius. Looking at the distance to horizon side, we take the distance of the radius plus the height squared minus the radius squared to determine the distance to the horizon squared, and then we get the square root of that to determine the distance from your eye position to the horizon. This straight line measurement will always be greater than the sea level point-to-point measurement based on the radius. This measurement is the arc mile, and we use the angle of the triangle to calculate this. We need to find the circumference and then determine the degrees per arc mile. The sums to find these figures are in these two sections, and it is based on the radius that has been entered. We need to convert the degrees to distance, and to do that we take the distance squared divided by the radius plus height squared from over here, and then we apply the asine function followed by the degrees function, and that figure is divided by the degrees per mile from over here to give the arc distance to the horizon. Moving over to the other side, and this is where we find the amount of fall. Using the angle which is derived from the arc distance, we first find the distance to the target, which is the straight line measurement that ends at the point where a right angle to the horizon, or parallel to the radius, intersects the circumference at the requested arc distance. The straight line horizon to target will always be shorter than the arc. Now we find this side of this triangle and subtract that from the radius to be left with the figure that represents the fall or drop. To find the hidden target height, we start with finding the line of sight distance and use that to determine the length of this side. Then minus the radius equals the hidden height. To find the measurements when looking to an object over the horizon, answers and equations from both sets of triangles are required. In order to display relevant results, it is necessary to create a second set of background formulas for some of the equations, and in the final result field of the calculator, we have an if function which allows this result to be relevant to either and or both sets of equations. You can find the horizon or the drop individually, or you can find both together. However, when finding both, the distance to the object that you input must be greater than the distance from the observer to the horizon in order to yield a result. When you subject my all-in-one calculator to the same accuracy test that I showed earlier, you see that the result is spot on. The math is already done, so just type in the 1/4 circumference measurement and you can see that the fall equals the radius as it should. This is true no matter what distance you set as the radius. I've created this calculator to display imperial measurements based on a radius of miles, but with a simple tweak to a couple of the fields and you're away with whatever reading you choose. I've already mentioned that the radius for this calculator is also adjustable. Therefore, this calculator can be used for all projects that require finding these measurements and need them to be accurate. Projects such as engineering designs for support structures or things with inner and outer circumferences, for example. But this function has another benefit, and that is that this calculator can be quickly calibrated to represent a body of water, such as a lake, that is on an elevated plane above sea level. By simply adding that elevation distance to the radius, we now have a new circumference, which essentially means that the lake is now the new sea level, as per the input of the longer radius, and because of the way these equations link up, feeding into or out of each other, it means that all the equations are derived from the current radius input. I've also made the file available on files.com where you can download it for free. I have left all of the equations visible so you can access the formulas for each cell and check that it is correct for yourself. Well, that's about it, and as I said earlier, I am no math genius, but I think I am right on this one. I welcome your feedback, so by all means, please review my all-in-one curve calculator and drop a comment below to let me know your thoughts. I sincerely hope that you found this video helpful in your search for the real truth, and if you did, then make sure to give this video the thumbs up and share it everywhere. Hit the subscribe button for more truth, click on the bell to set notifications, and definitely check out my other videos to get up to speed. If you have other related material that you would like to share, you can send it to rightsideupcontributions@gmail.com. Thank you for watching, and remember to search with an open mind, share what you find, and together, let's get everyone right side up.